Welcome to Lesson 10, Object-Oriented Programming. So far, you've mostly written Python as a sequence of instructions, variables, functions, and scripts. That works well until a project grows. Too many moving parts, too many assumptions, and code that becomes hard to extend without breaking. OOP is Python's way to scale. Instead of thinking only in actions, you start thinking in things, objects that bundle data together with the behaviors that operate on that data. The three pillars are straightforward. A class is a blueprint, an object is an instance created from that blueprint, and methods are functions attached to the class that act on the object's internal state. Master these, and you'll be able to turn messy scripts into clean, extensible systems.
And it's more practical than it sounds. You've already been using OOP since day one. Strings, lists, and dictionaries are objects, and their methods are exactly the kind of built-in behavior OOP gives you. The real advantage is organization. Instead of passing lots of variables around, you keep related data together and expose only the operations that make sense. That reduces mental load, improves readability, and makes your code easier to reuse across projects. Even in data analysis, OOP helps you build pipelines that stay clean as they grow, especially when you combine it with robust error handling from the previous lesson.
In this lesson, we make a clean jump in how we structure Python code. Until now, most programs could be written as variables, functions, and a linear script. That is fast and perfectly fine. But when code grows with more steps, more options, more data sources, and more edge cases, a single script starts to fight you. It becomes harder to change safely and harder to see what belongs to what. Objective 1 is to understand what a class really is in practical terms. A class defines a new type in your program, something with a clear structure and predictable behavior. Think of it as a blueprint for creating objects that share the same shape. Real projects repeat patterns: a dataset with metadata, a configuration, a model with parameters, a report with sections. Classes let you represent those patterns explicitly. Next, we will create objects from classes. An object is one specific instance with its own internal state. You can create multiple objects from the same class, and each one keeps its own data. This shifts you away from scattered variables and toward one entity, one place where state lives. Then we introduce $init, written as $init and instance attributes. This is the setup step that gives a new object a valid starting state. Instance attributes are the object's own data, the values that make one instance different from another. Finally, we focus on judgment, recognizing when object-oriented programming is useful. Do not force it everywhere. If a tiny script does the job, keep it simple. But if something will evolve over time, with repeated operations and multiple responsibilities, classes give you structure at scale. The goal is not fancy code. The goal is maintainable, understandable, reusable code as your projects grow.
Let's connect these objectives to real work. Picture a small data pipeline. Load data, clean it, compute features, export results. At first it is just a few functions. Then you add variations, new file paths, new column mappings, new filters, different output folders. Suddenly you are passing many arguments around, relying on global variables, or copying and pasting logic into slightly different versions. That is the moment code starts to feel messy. A class helps because it creates a clean container for a concept in your program. For example, a data cleaner object can know which columns to keep, how to handle missing values, and how to validate the output. Instead of spreading that knowledge across disconnected functions, it lives in one cohesive component. Creating objects from the same class gives you reuse without copy-paste. One cleaner can be configured for dataset A, another for dataset B, with the same blueprint. $init and instance attributes also improve safety. You can design an object so it cannot exist in a broken state. If a required file path is missing, or required columns are not provided, you can fail early with a clear message. And the last objective is the most important. Use object-oriented programming when it reduces complexity, not when it adds it. For a 20-line script, a class may be pointless. For something you will run repeatedly, extend over months, or share with others, classes turn a sequence of commands into well-defined components you can test, reason about, and evolve with confidence.
Up to this point, most Python programs can be described with two basic building blocks. Variables store data, and functions describe actions you want to perform on that data. That is already enough to build a lot of useful scripts. The problem appears when the project grows. Data is rarely just one value. It becomes a small ecosystem, a dataset plus its path on disk, plus column names, plus validation rules, plus derived metrics, plus a history of transformations, plus warnings and errors. If you keep adding separate variables and separate functions, you often end up passing many arguments around, repeating the same checks, and losing track of what belongs together. Object-oriented programming exists to solve that organizational problem. A class lets you group data and behavior into a single, coherent unit. Instead of having a loose set of variables and a loose set of functions, you define one concept, give it a name, and attach the relevant operations to it. That creates structure and reduces accidental complexity. So the main idea here is simple. Variables describe data. Functions describe actions. Classes bundle the two together so you can work at a higher level of abstraction. This is how Python moves from small scripts to systems you can extend, test, and maintain.
A practical way to feel this is to imagine a tiny data analysis pipeline. At first you have a file path, you load a table, you clean it, and you compute a couple of results. Easy. Then reality arrives. The file path changes. Some columns are missing. Dates come in multiple formats. Some rows are malformed. You need to log what happened. You want to store intermediate results. You want to reuse the same pipeline tomorrow on a different dataset. If everything is just separate variables and separate functions, you start juggling lots of pieces. A class gives you a place where those pieces can live together. The object can remember its own state, like where the data came from, what cleaning steps were applied, what assumptions were used, and what errors were encountered. And the methods are simply the actions that make sense for that object. This is why the idea matters. It is not about writing fancy code. It is about reducing chaos when your program has multiple moving parts. Once you feel the pain of scattered state and repeated glue code, classes become a very natural tool.
Let us make the vocabulary precise, because object-oriented programming is mostly about clear mental models. A class is a blueprint. In Python, when you write class person, you are defining a new type, just like int or str is a type. You are telling Python, from now on, there is a new kind of thing called person. At the beginning, a class can be empty. The keyword pass is simply a placeholder that means no attributes and no methods yet. The class exists, but it does not do anything. Naming matters. By convention, class names use camel case, so person is a typical class name. This helps readability, because you can immediately recognize what is a class versus a variable or a function. Once you have a class, you can create objects from it. The expression person with parentheses, person open close parentheses, is a call that creates a new instance. If you assign it to a variable like p equals person, then p refers to a concrete object in memory. So here is the key distinction. The class is the blueprint, the general definition. The object is one specific instance built from that blueprint. And you can create many different objects from the same class, each one with its own data and its own state.
Think of it like a stamp and the things it produces. The stamp design is the class. Each stamp coin is an object. They come from the same design, but each coin is a separate physical item. In code, that means you might create p equals person, and later create q equals person. Both are persons, so they share the same type, but they are not the same object. If you later add attributes, p could store one name and q could store a different name. Also notice the role of the variable name. P is not the person itself. It is a reference, a label that points to the object. You can have multiple labels pointing to the same object, and you can also reassign a label to point somewhere else. That is why people say variables in Python are references. For now, the example is intentionally minimal. The purpose is to separate the concepts cleanly. First you define a class, which is a type. Then you instantiate it, which gives you an object. Next, we will start giving the class real content so the objects become useful.
Now we give the class real content, and the key tool is the method named $init_. Conceptually, init is the initialization step for a new object. When you create an instance by calling person with parentheses, Python immediately calls this init method to set up the internal state of that brand new object. Look at the signature. The first parameter is self. Self is not a special keyword, but it is a strict convention. It represents the current object that is being created, the specific instance that the code is configuring. When you write self.name, you attach an attribute called name to that object. When you write self.age, you attach an attribute called age. The other parameters, name and age, are the inputs you pass at creation time. So init is the bridge between external values, like a name and an age, and internal attributes stored inside the object. A critical idea is that these attributes live on the object, not inside the class definition as global variables. Each instance gets its own copy. That is why two different person objects can have different names and ages. So the class is the template, init is the setup procedure, and self is how the method talks to the specific object being built.
The bottom example shows the whole story in one line. When you write p equals person with Michelle and 40 inside the parentheses, you are not just calling a function. You are asking Python to create a new person object, and those values are handed directly to init. Inside init, self refers to that new object, and the assignments create its fields. After the constructor finishes, p points to an object that now has p.name equal to Michelle, and p.age equal to 40. This is why init is so central in object-oriented programming. It is where you define what information every instance should start with. In real projects, this might include validation, default values, or transforming inputs into a clean internal form. One practical tip: if you forget self in the parameter list, or you forget to prefix attributes with self. Python will either raise an error or you will accidentally create local variables that disappear when init ends. So when debugging classes, always check two things first. Self is present in the signature, and attributes are written as self.something. With that in place, objects stop being empty shells and become structured containers for data that can travel together with the behavior you will add next.
Here we move from creating an object to actually using what we stored inside it. When you build an instance, you are packaging data into a single, named entity. After that, you access that stored data through the attribute system. The key idea is simple. The object keeps its own internal fields, and you can retrieve them whenever you need. This is one of the reasons object-oriented programming scales well. Instead of carrying separate variables around, you carry one object, and the object carries its data. In practice, you often create an instance, then immediately read its attributes to display them, to compute something, or to make decisions. Think of attributes as labeled values attached to the object, like name and age. Once they exist, they can be reused in many places without recalculating or reparsing anything. This is also where consistency matters. If you always store the same attributes for each instance, your code becomes predictable. You can write functions and methods that assume those attributes exist, and your program becomes easier to maintain.
From a practical point of view, this slide is showing a common workflow. First, you create a person object with two pieces of information, a name and an age. Then you read those values back out and print them. The important part is that you are not printing a separate variable. You are printing the value stored inside the object. That is why the .access pattern is so powerful. It tells Python, go into this object and fetch the field called name, then go into the same object and fetch the field called age. Once you can do that, you can do much more than printing. You can build messages, compute derived values, compare people, or pass the object to another function that needs the same data. One common beginner mistake is a spelling mismatch. If you store an attribute with one name and later try to access it with a different name, Python will raise an attribute error. So when debugging, always check that the attribute was created in the initializer, and that you are using the exact same attribute name when you access it.
So far we use classes to store data. Now we add the second half of the idea. A class groups data and behavior. Behavior lives in methods, which are functions defined inside a class. The key shift is that a method is designed to operate on an instance. That is why it receives the instance as its first parameter, conventionally named self. Self is not magic. It is simply a reference to the current object, so the method can access the object's attributes and use them to do something meaningful. Once you define a method, every instance created from that class can call it. This gives you a clean way to express actions that belong to that type. Instead of writing separate functions that take a person as an argument, You attach the action to the person itself. This is the core advantage of object-oriented design. It keeps related code together, it reduces scattered variables, and it makes your programs easier to extend. When you read code like speak, you immediately understand that speaking is something a person object can do, and that the method will probably use the person's internal data to produce a result.
In the example, the class defines a method called speak. Inside that method, it prints a sentence that includes the person's name and age by reading self.name and self.age. In other words, the method is reaching into the object and using its stored attributes to generate output. Then, when you call p.speak, you are telling Python to run that method on that specific instance. Under the hood, Python passes p as the self argument automatically. You do not type self when calling the method, but the method still receives it. That is why the same method can behave differently depending on which instance calls it. If p is Michelle age 40, the message will reflect those values. If another instance has different attributes, the output changes without you rewriting the method. This is exactly what people mean when they say objects have both data and behavior. You store the state in attributes and you expose actions through methods that use that state.
Encapsulation is the idea that an object should protect its internal state and expose a controlled interface to the outside world. In practice, this means you do not want random parts of your program to freely change important attributes in ways that break your assumptions. Instead, the class decides how its data can be read or modified. This becomes valuable as soon as your objects represent real entities with rules. For example, an age should be a non-negative number, a name should be a non-empty string, and maybe a person cannot suddenly become younger if your application logic forbids it. Encapsulation is not about making things secret for the sake of secrecy. It is about reducing accidental misuse and keeping the class responsible for its own consistency. In Python, encapsulation is mostly a convention, not strict enforcement, but the pattern is still extremely useful. It encourages you to design clean boundaries, so your code stays predictable and easier to maintain as it grows.
In the code, attributes like _name and _age are meant to be treated as internal. The underscore is a signal to other developers, including your future self, that these fields should not be accessed directly. Instead, you provide methods that act as the public interface, such as getName or setAge. A getter returns the value, and a setter updates it, but only after applying checks. So a setAge method could reject negative values, reject non-integers or log changes. That is the real point. You are not just hiding data, you are controlling access. The example also shows how the outside code interacts with the object through methods. You create the instance, then you call a method like setAge to update it. This keeps the logic for validation inside the class where it belongs, and it prevents your program from silently drifting into invalid states.
Inheritance is a way to build a new class by reusing and extending an existing one. You start from a base class, sometimes called the parent class, and you create a derived class, also called a child class. The key idea is that the child class automatically gets the attributes and methods of the parent, so you do not rewrite the same logic again and again. Conceptually, this models and is a relationship. An employee is a person plus something extra. In real projects, inheritance is useful when many classes share a common core, like name and age, but each specialized type adds its own data or behavior. The important detail is that you want the shared parts to live in the parent class and the differences to live in the child classes. That keeps the code consistent and reduces bugs caused by duplicated logic. In Python, when you use inheritance, you typically call the parent constructor from the child constructor, so the base attributes are initialized in one single place. Then you add the new fields that belong only to the derived class.
In the example, you have a person class that represents the shared information, and then an employee class that extends person by adding a salary. The way you connect them is by writing employee with person in parentheses, which tells Python that employee inherits from person. Then, inside the employee constructor, you call super to run the parent constructor. That call is what sets up the inherited state like name and age, exactly as person defines it. After that, you assign the employee-specific attribute salary. This pattern is crucial because it prevents you from re-implementing the same initialization rules in every subclass. Finally, when you create an employee object, you pass the arguments needed for both levels, the person part and the employee part. The resulting object can be used like a person because it has all the person methods and attributes, but it also has the extra features that make it an employee.
Polymorphism means that the same method name can produce different behavior depending on the type of object you call it on. In object-oriented programming, this is one of the biggest reasons to use inheritance at all. You define a common interface in a base class, like a method called speak, and then each subclass can provide its own version of that method. From the outside, you still call speak the same way, but Python decides which implementation to run based on the actual object. This is powerful because it lets you write code that is general, clean, and scalable. Instead of checking types manually with if statements, you trust the objects to know how to behave. So the code becomes focused on what you want to do, not on what specific object you have. In practical terms, polymorphism is what allows you to treat different objects in the same collection in a uniform way, while still getting specialized behavior for each one.
In the slide, person and employee both provide a speak method, but employee overrides it to add extra information, like the salary. The important point is that you can put both objects into the same list, even though they are not exactly the same class because employee is still a kind of person. Then you loop over the list and call person.speak for each element. You never write a special case for employee. You just call the same method name, and each object responds with its own version. That is polymorphism in action. It is also a major code quality tool because when you later add a new subclass like student or manager, you can drop it into the same list and the loop will still work as long as that class implements speak. The loop does not need to change, only the new class does.
This slide shows the core difference in mindset between functions and object-oriented programming. A function is usually about an action. You pass inputs in, it performs a task, and it produces an output or a side effect. That approach is perfect when the logic is simple, isolated, and does not need to remember anything beyond the current call. Object-oriented programming, instead, is about modeling entities that have both data and behavior together. The key idea is that when data and the operations on that data naturally belong together, you can bundle them into a class. That gives you structure, consistency, and a place where responsibilities live. In small scripts, functions are often the fastest and cleanest solution. But as projects grow, you often want code that is easier to extend, easier to reuse, and harder to break accidentally. OOP helps because it creates clear boundaries. It also makes it natural to add features without rewriting everything, because behavior can be expanded with new methods, and shared logic can be organized in base classes.
On the left side, you have a greet function that needs name and age every time you call it. That works, but it means the data is always external, and you must keep passing it around. On the right side, you build a person object that stores name and age once inside the instance. After that, greet becomes a method so it can access those values through self. The call becomes simpler because the object carries its own state. This also changes how you scale the code. If later you want to add more related behavior, like updating the age, validating the name, formatting the output, or adding more attributes, the person class becomes the natural home for those changes. With only functions, you might end up with many separate functions that all need the same parameters, and the risk is that the interface becomes messy. The main takeaway is that both tools are valid in Python. Use functions for small, focused pieces of logic. Use OOP when you are describing real entities and when data and behavior should stay together.
That wraps up Lesson 10 on object-oriented programming. The big goal was not to memorize syntax, but to change how you think about code when it starts getting bigger. You saw the basic building blocks: classes as blueprints, objects as concrete instances, attributes as stored data, and methods as behavior tied to that data. You also saw why that matters in practice. When data and behavior naturally belong together, classes give you cleaner structure, clearer responsibilities, and code that is easier to extend without breaking everything else. In short, OOP is one of the main tools Python gives you to move from quick scripts to systems that stay readable as they grow.
If you want to practice, the best exercise is to take something you would normally write with a couple of functions and ask, is there an entity here that has state and actions? If yes, try turning it into a small class with 2 or 3 attributes and 1 or 2 methods. Keep it simple and focus on clarity. In the next lesson, we will shift from just writing correct Python to writing Python that feels natural. Lesson 11 is about becoming more Pythonic, meaning you will learn idioms and habits that make your code cleaner, shorter, and easier to read. And if you want more exercises to reinforce everything, you can find practice material on mitchellperry.com.